Hello everyone and welcome back to L582, Modeling and Control of Electric Machines and Drives. In our last lectures we've been talking about the testing of three-phase induction motor to determine the equivalent circuit parameters of this machine so we can use it for any performance calculation related to the machine using the per-phase equivalent circuit seen here. We started with the DC test and locked rotor test, and from those tests we figured out how to find the resistances of the stator and rotor R1 and R2 and the reactances of stator and rotor X1 and X2, and then go into the no-load test to figure out the core representation, which is RC and XM. Like we've seen here, like we said, the no-load test is basically what we do is we make the shaft no-loaded. That means we do not connect the shaft of the motor to any mechanical load and just let it run freely. So the motor is not really driving any load, okay? So all the power that the machine will draw is basically going to losses because there is no power converted to load power, to mechanical power to feed the load. So everything is just the internal machine losses, okay? Like we said, as with no load, the machine just speeds is very high, so it's very close to the synchronous speed. It's almost equal to the synchronous speed, but a little bit less than it. Like we said before, it cannot exactly equal the synchronous speed, otherwise there will not be relative speed between the rotor and the stator, and that means there's no change in the magnetic field seen by the rotor, and this will just blow out the machine's torque because, you know, the machine whole theory of operation depends on this induction. That means there is induced voltage in the rotor coming by seeing the stator flux time changing, and this will not happen if the rotor actual speed is just at the same as the magnetic field rotation of the stator, which is the synchronous speed. So the mechanical speed is less than the synchronous speed, but if the machine is not loaded, this mechanical speed is very, very close to the synchronous speed. And that means your slip, which is the difference between the two speeds divided by the synchronous speed, is almost zero, and this will give you a very high push here in your R2 over S here. So the slip almost equals zero. That means R2 over S will be very, very big, okay? And like we know that X2 and R2 over S, which is the rotor impedance, is in parallel with the core impedance RC and XM, which is by definition very high values, RC and XM. So, but yeah, still now R2 over S is very, very high compared to those guys, and they are just connected in parallel. And you know, for any two impedances connected in parallel, the equivalent of them will be very close to the smallest one if you have a very small one and a very big one connected in parallel. So here the equivalent of them will be very small to RC and XM because, you know, R2 over S is now very, very big. So we can ignore the rotor impedance R2 over S and JX2, and the equivalent circuit will be just looking like that. If we are talking about the exact equivalent circuit, means we have RC represented in the circuit. If we are talking about the approximate equivalent circuit, where RC is not here anymore because we are just assuming that the core losses, which is represented by RC here in the equivalent circuit, in the exact equivalent circuit, is constant loss. It does not change with the change in the current and the load, okay? And that's what we call the approximate equivalent circuit, okay? So it depends on which circuit you're dealing with here. So we started talking last time, if we're talking about the approximate equivalent circuit, this guy here, and just we said like that. Here, like any other test, we are just measuring the voltage, current, and power taken by the machine at these conditions. And just to remind you that the no load losses, no load power, or here no load test, is just done at the rated voltage of the machine, okay? Why? Because again, that is the typical condition where the machine works at, so we want the machine to be at the same condition in order to get the equivalent circuit parameters as accurate as we want it to be, okay? So the power is taken by the machine here is basically the power losses going into the machine at this condition, which is, as you've seen here, is basically part of it will be copper losses in the stator resistance R1, which is 3I no load square R1. And still there's two other power losses is not represented in this equivalent circuit because we're assuming they're constant, so no need to represent them by resistances in the equivalent circuit. which is the core losses and the rotational losses. Okay, the core losses we are just assuming that's constant here because that is our approximate equivalent circuit. Okay, so here we combining rotational losses and core losses together. We don't need to just separate them because there is no actual need for this because we're just assuming both of them are constant losses. So so they're combined together here. If you want to find them, you basically have P no load minus 3I no load square R1, and this will give you the combined core and rotational losses which you need for your power flow diagram and calculations of the machine's efficiency. Okay, and after this we need to find XM here in this equivalent circuit. That is our last equivalent circuit parameter we don't know, so we will just go with our P, which is equal P no load equal 3 V no load I no load cosine theta no load. Everything here is known except for theta no load, so you can find it and then use it using these to find Q no load. It will equal P no load tan theta no load. And from the Q, that is the Q going to this circuit, you have two reactances, and you know the Q is just going to the reactances. X1 and XM both are just connected in series, like you see in here. So Q no load will basically equal 3I no load square X1 plus XM. Everything is known here except for XM, okay? And this, you can find XM here, and now you have everything in hand. Okay? That was the idea. We're just having the approximate equivalent circuit. But what about if we are just dealing with an exact equivalent circuit like here? That means we have RC. We're not assuming that the core losses is constant and just lumped with the rotational losses. Now it is represented by a resistance in the equivalent circuit, which is RC. Now we are dealing with different thing. Okay? So we need a little bit different approach to just deal with here. Okay? So let's now assume that we are dealing with exact equivalent circuit. So I'm gonna say, what about the no load test for exact equivalent circuit? Okay, so that means for now our equivalent circuit will look like that. That is R1 and JX1. And now that is your core representation. Now you have RC and XM, not just XM like in the approximate equivalent circuit. Okay? And here is your V no load, which I just suppose you know that is equal the rated voltage of the machine. Okay? And here is your I no load going here. Okay? So the same idea. We have just measured from the test the P, which is P no load, and the voltage V no load, which is the rated voltage, and the current, which is I no load. Those are measured values. Okay, and you just have to use them to find the the exact equivalent circuit parameters here, which is RC and XM. That's a little bit tricky here, so let's do the same what we were doing before. Say what this power, which is just you have measured here, will represent. That is the active power, guys, so it's going to the resistances. Okay, so the power here going to the resistance is the only resistance here, which is R1, so it is 3 I no load square R1. And I don't need to remind you, here is just everything is just in magnitudes. Anyway, you're just measuring the magnitude of the current using an ammeter, so you don't need this, but I'm just reminding you that when you're just dealing with powers and everything, you just calculating with magnitudes. So the P no load is 3 I no load square R1. But and you still have other resistance here, which is RC. It's the power going there also. Okay, so I'm gonna use the voltage on its terminals now. I'm gonna say that this voltage over those terminals here, I will call it here E2. And you know that is the voltage of the rotor, which is the same like the voltage, so the same points connected to the rotor, which is E2 here. So the power going to this resistance RC here will be 3 E2 as a magnitude square divided by RC. You know that the power going to resistance can be 3 I square R or 3 V square over R. Okay, so that is 3 E2 square over RC. And don't forget, please, that you still have the friction and windage losses or the rotational losses or the mechanical losses, because it's not represented in the circuit here by any resistance, but it's a constant loss, you still have it in your hand. So don't forget it, okay? So this power going to RC is your P core now, which is not constant here. It depends on the just whatever this current I load changes, this voltage E2 will change, and this will change this value 3E square over RC. That's why I'm saying for the exact equivalent circuit, the core losses is not just assumed to be constant anymore. With any change in the load, that will change the current, and this changes the voltage E2, and this changes the core losses here. So it's different, okay? So for here, we have the P friction windage rotational losses and the core losses. They are not lumped now anymore. They have to be separated, okay? So let me just say for here that first you'll have P no load here and just say minus 3I no load square R1, okay? That will equal P core plus P friction and windage, okay? Everything here is known for you. P no load is measured, I no load is measured, and R1 you know it from the DC test, okay? So you have those lumped together, and now we need to separate them because they are not just lumped anymore, okay? So you use this to find the P core plus P friction and windage, okay? How to separate them, that is a question here. Separating them, guys, needs a little bit of work. The whole point is, I'm gonna do this here. So using this, you'll just do this gradually. Reduce the applied voltage to the machine while it's a no load here, okay? And okay, recalculate P core plus P friction and windage at each voltage value, okay? And you basically have a graph like that. Here is your P friction windage plus P core, and here is your voltage, V no load, you're applying to the stator, okay guys? What I'm doing is you'll start from the rated value here, so that is the V rated, okay? And just record the value for those guys together, and start reducing this voltage a little bit, okay? This reduction, so the voltage is reduced as much as we can without letting the machine stop, okay? So you're reducing the voltage as much as you can, but you know, with the reduction in the voltage, if you just go very low, the machine will stop. So you just reducing the voltage as much as you can, and this will give you this curve here like that, okay? So typically this value, as less as you can go here, will be a 30% of the V rated, okay guys? It's different from machine to machine, but it will be around 30% of the rated voltage, okay? So you keep going down and down like that, okay guys? After this, you just do interpolation to the rest here until you hit the 0 voltage here, that is 0 volt, okay? So you do here extrapolation, okay? That means you just follow the same pattern of reduction here, but just mathematically like this until you hit the vertical axis, and this will be your friction and windage losses, PFW. Why? Because like we know before, if you remember, that is the core losses is just depends on the magnetic field, magnetic flux, okay? And for you to know that the magnetic flux depends on the voltage applied to the machine, okay? So if the voltage is 0, that means theoretically no flux, and that means theoretically no core losses, okay? So that's the whole point of doing this. If you extrapolate this curve until you hit the 0 voltage, that means you're guaranteed at this point that the core loss will just disappear, because No voltage, that means no magnetic field, and that means no core losses. And that's the whole point. We can just have the friction and windage losses and core losses lumped together and just keep doing with them. But if we need to just separate them, we need to hit a point where one of them equals 0, so the rest is just what we have in hand. So that's the whole point of doing this. Keep reducing the voltage applied to the machine as much as you can, and just extrapolate this curve to hit the 0 voltage. And for the 0 voltage, theoretically no flux, and this means theoretically no core losses. So this point will give you the friction and windage losses, and that's it. Okay, guys? So from here, you get your friction and windage losses. Okay? So again, back to the power. So you know that the P no load equals 3 I no load square R1 plus the P friction and windage plus the core losses. And the core losses here equal 3 E2 as a magnitude square over RC. Okay, guys? From here now, we have everything. We have P no load that is measured. I no load is measured. R1 from the DCA test. Friction and windage losses are now known from this experimental extrapolation test we did. So everything is in hand here. You can just find the core losses. This guy. Okay, guys? That's it. So from here we can find the core loss, okay? But we don't need to find the core losses as a value here. We need to find RC specifically, okay? So we can easily find the core losses, the RC here if you know E2, okay? Because everything here will be just known, if you know. So the whole point here, you need to find the rotor voltage, E2, at this condition. How to find this? Going back to the circuit. That is R1, JX1, and here is your core representation, RC, and JXM, okay? Again, that is V no load, that is I no load, okay? And here is your rotor voltage, E2. Okay, guys? How to find this? Easy enough. You can find it from the circuit, but keep in mind that now to find everything here, you're dealing with an AC circuit, so everything to be calculated for the voltages, if you want to find V, has to be in magnitude and angle. So how to find this angle of the current here, because it's not measured, you can just calculate it like we said before. So the power going to this circuit, I'm gonna call it P circuit, will equal no load power minus the friction and windage losses. You know that, okay? So you have the total power here in the no load condition. So a part of it will go to this resistance R1, a part going to this resistance RC, but still the friction and windage loss is not included in the circuit, so do not forget it, okay? So here P circuit equals P no load minus P friction and windage, okay, guys? And you know V no load and I no load. So from them easily you can find the angle, okay? Because you still have the same thing. So you know that the P circuit here will equal 3 V no load I no load cosine theta no load, okay? P circuit has just found from here because you know both of those guys. P no load is measured and P friction windage we have just calculated using our test. V no load and I no load are known, so you can just find theta no load easily, okay? So you have theta no load in your hand. This is the angle of both the power and the current, okay? So theta no load will be just the angle of your current also. So the current will be I no load and angle theta no load. We know that, okay? So if you need to find this voltage E2 from the circuit here, it will be now easy. E2 as a magnitude and angle, okay, is theta, call it theta E2, will equal the V no load as a magnitude and angle, and the angle of the voltage, we always make it our reference, which is 0. So that's V no load, magnitude and angle, minus the current, I no load as a magnitude and angle, which is theta no load, we just found it from here, multiplied by those R1 plus JX1. regular Kirchhoff voltage law, guys. R1 plus JX1. Okay? If you know, everything here is known. Okay, and this will just give you to calculate E2. So everything is known. X1 is known, R1 is known from the previous tests. Theta no load is just known now by this calculation we just found. I no load is measured, V no load is measured, and it's the rated voltage. So everything is known here. You can find E2 as a magnitude and angle, and we don't need its angle actually, we just need the magnitude. So everything here is known except for our E2 magnitude we need here in our core losses calculation, if you remember. Okay guys, so from here we can find everything. Okay, again, because P no load equals 3 I no load square R1 plus P friction and windage plus 3 E2 magnitude square divided by RC. Okay, P no load is measured, I no load is measured, R1 from DC test, P friction windage we just found it by calculation extrapolation. E2 is now known as a magnitude just from here. So everything here is known except for RC, and that's what we need here to be calculated. Okay, so now you know how to find RC. That's it. Okay guys, what about XM? You should be known now. That is the same thing, easy enough. So to find Q no load, you need to multiply P no load by 10 theta no load, and both of them are known now. You know that the Q go to the axis in this circuit, which is X1 and XM. So it will be the same thing. It is 3 I no load square X1 plus the Q going to XM, which is the same thing, 3 E2 as a magnitude square divided by XM. The same thing, guys. Okay, so again, everything here is known. Q no load had just measured now, we just found it from here. I no load is measured, X1 from the block rotor test. E2 magnitude we just found by our calculation, so everything is known except for XM, so this guy can be calculated here. Okay guys, so should be the same idea we did before, but it's just the whole point is what's in your hand and what can you be calculated and all that stuff. It's a little bit trickier than using the more easily approximate equivalent circuit, but it's still not that complicated if you need to deal with it. Okay, the good news, most of the time we're dealing with the approximate equivalent circuit, not with the exact equivalent circuit, but you are forced to deal with it. You can go with it. Okay guys, okay, by the way, in your lab you're dealing with this, with the exact equivalent circuit, because we have already done this test to separate the friction windage losses and the core losses. So in your lab reports you need to do this with the exact equivalent circuit, but most of our solved problems and all that stuff will be dealing with the approximate equivalent circuit most of the time. Okay, or not, but yeah, so the approximate equivalent circuit gives a fairly accurate results. Okay, so yeah, most of the time we stick with it, but still, if you need to go with the with the exact equivalent circuit, we now learned how to deal with it like we just said here. Okay guys, okay, now we should be having all our equivalent circuit parameters here, so you now should be known everything, R1 and JX1 and JXM, if this is an approximate equivalent circuit, and that is JX2, and here's R2 over S. Okay, that is your approximate equivalent circuit. Will be dealing with most of the time, like we said before. And you should now know all those. You know R1, X1, X2, R2, and XM. So this circuit is now unique for your own machine, and you can just deal with this to find whatever you need about your own machine. Okay. For example, I'm gonna jump over here to the next item on our list. If you remember with all the machines we dealt with before, we go to the construction and then theory of operation to understand how the machine works, and then we just had our equivalent circuit, studied it, and find our power flow diagram, and then jump it to the equivalent circuit parameter determination like we said here. And after this, we go to the torque speed characteristics of the machine, or how to use this equivalent circuit to understand how the machine actually operates. So that's what I will be jumping to find here. Okay, so I'm gonna go to another one here. Okay, and I'm gonna start talking about the torque speed characteristics of the three-phase induction motor. Okay, torque speed characteristics of the three-phase induction motor. How to calculate the machine's torque. I've already just said this before. So for any kind of a machine, to find the electromagnetic torque developed with the machine, it equals the converted power divided by omega m, to the mechanical speed in radian per seconds. Okay, so that is your torque, which is the electromagnetic developed torque. Okay, that is the converted or developed power, which is converted from electrical to mechanical power here, because we're talking about a motor, don't forget. Omega m is the rotor speed in radian per seconds. Okay, by the way, do not confuse this with the output torque, because that's different. That is the electromagnetic developed torque, which is the converted inside the machine. But the output torque output, or sometimes we call it the shaft torque, they are the same, all equal the output power divided by omega m. This output power, sometimes we call it the shaft power, P shaft, they are the same thing. So the output torque, or the shaft torque, you need to divide the output power, the shaft power, by omega m, not the converted power. And you know, the difference between them is the friction windage losses, your rotational losses. So the P shaft is basically, or the P output, equal P converted minus P friction and windage, you know. So this difference will make a difference in the torque. But the more we stick with is this torque, which is the developed torque, because that's the thing we can just deal with inside the machine, that's the thing we have in hand. Because in all the friction and windage losses, we cannot calculate it like calculation. It's just found in the lab like we did just a minute ago. Okay. So we stick with the electromagnetic developed torque, torque m, we call it the machine's torque, or the electromagnetic developed torque, which is P converted over omega m. Yeah. But you know, for this machine, and refer back to previous lectures we don't remember, that the converted power can be calculated like 1 minus s multiplied by the air gap power. And omega m by definition equals 1 minus s omega s, which is omega s here is your synchronous speed. It's the synchronous speed in radian per second here. Okay, so 1 minus s goes with minus s, and you still now with air gap power over omega s. Okay, so for our three-phase induction machine, the motor torque, or the electromagnetic torque, can be found by the converted power over omega m, or from the air gap power over omega s. It's up to you, and up to the data you have in your hand. Okay, if you refer back again to our power flow diagram and with the calculation there, the air gap power can just be found by 3 I2, which is the rotor current, as a magnitude square R2 over S. It is the power going to the R2 over S resistance. Okay, because of the whole power going from the stator to the rotor, remember? Okay, so here is your rotor circuit, here is your rotor circuit, and here is your stator circuit. Okay, and between them here, that is the air gap, so that is the P air gap going from the stator to the rotor here. So the power going to this circuit, and we know the power in the circuit is just represented in R2 over S, and all just the resistances. Okay, so the power here, P air gap, equals 3 I rotor square R2 over S. Okay, and that means if we just go in here and just remember that the torque equal P air gap over omega S, so the torque of the machine can be just represented like 3I2 as a magnitude square R2 over S omega S. Okay, because just divide this power by omega S to find the torque. Okay, guys? And now we know how to just deal with the torque and find it. All when we know here the torque speed characteristics is have a relationship between the torque and the speed or the slip, because you know the slip is just a representation for the speed, whatever it is. Okay, so we need to have something to deal with here, but we don't need to see the current, because the current is another thing to be calculated. It's not something constant to deal with. Okay, so we need to just refine this equation to be more representative. Okay, guys? But yeah, it just should be the same idea we did before. Okay, so how to derive this? I'm gonna do something like that. We need here to derive the Thevenin equivalent circuit of the three-phase induction motor. Okay, how this? Remember our approximate equivalent circuit we're dealing with most of the time, like I said, R1, JX1, and here is your JXM, and here is your rotor circuit, JX2 and R2 over S. We need to find the Thevenin equivalent circuit over the rotor terminals, those terminals. Okay, we need to find the Thevenin equivalent circuit over here. That means I need to take out all the stator and the core representation, those guys, and just represent them by a Thevenin equivalent circuit. Thevenin. If you refer back to your Thevenin equivalent circuit you have back in your circuit courses, that means I'm gonna take this guy, which is, you know, there is a voltage here V1, the voltage applied to the stator terminals, you know that. The Thevenin equivalent circuit will be basically you're taking out this circuit and represented by the Thevenin equivalent circuit, which is basically a voltage source V Thevenin and Thevenin impedance, which are Thevenin and JX Thevenin. This is what we call the Thevenin equivalent circuit. Okay. So yeah, we need just to find the equivalent of this guy and just replace it by this Thevenin equivalent circuit to just simplify our calculation. Okay, how to do this? I'm gonna refresh your memory very fast now about how to calculate the Thevenin equivalent circuit. Okay, so finding the Thevenin equivalent circuit, you need to find the voltage of Thevenin, Thevenin voltage, V Thevenin, and the impedance, R Thevenin plus JX Thevenin. How to find the Thevenin voltage? So that's the start here. So finding V Thevenin is basically the open circuit voltage at the required terminals. Okay, so that's the definition of a Thevenin voltage. So those are your two terminals you need, those red dots here, those are the terminals you need. So that means open circuit at this terminals and find the voltage here, and this will be your Thevenin voltage. Easy as that. So I'm gonna just have it drawn here. So I'm gonna open circuit the circuit at those guys. So that means here we find it R1, JX1, and here's your JXM, and we open circuit it at those terminals we need to find V Thevenin at, and that means here's your V Thevenin. Don't forget that you have voltage applied here to the stator terminals V1. Okay, so easy as that. To find V Thevenin from here, it will be just the voltage divider, because all of those R1, X1, and XM, they are all in series now because we just open circuit the terminals. Okay, so V Thevenin will be equaling V1 multiplied by JXM divided by the summation of all of them, R1 plus JX1 plus XM. Okay, guys, it's basic circuits. So that is how you can find the Thevenin voltage, V Thevenin. Okay. What about the Z Thevenin, the impedance of Thevenin, which is R Thevenin plus JX Thevenin? So to find that Thevenin, which is basically R Thevenin plus JX Thevenin, it is the impedance of the circuit seen from the required terminals after making the circuit passive. What I mean by a passive circuit? The passive circuit means you get rid of the sources, okay? The voltage sources, you make them short circuited, and the current sources, if you have any, you make them open circuits. That is how you make the circuit passive. You get rid of these sources. Okay? So we have a voltage source here, which is V1. So to find it, we need to make this voltage source a short circuit and look from the terminals here to find the equivalent impedance. Easy as that. So that is your circuit. JX1, R1, and now I'm placing a short circuit here instead of our voltage source V1. Okay, guys? And here is your JXM. And here's your terminals. And you just look from here and try to find the equivalent impedance. Easy as that. Okay, looking from here will make you R1 and X1 are just in series, and both of them in parallel with JXM, like you've seen here. So Z Thevenin will be just JXM in parallel with R1 plus JX1. Okay, guys? You can find this easily. Two impedances are just in parallel, so Z Thevenin will be equaling the multiplication of them, JXM multiplied by R1 plus JX1, divided by the summation of them, which is now R1 plus JX1 plus XM. Okay, guys? So this is your Z Thevenin. Easy as that. Okay? Because everything here is known. R1, X1, and XM, they are all known from your equivalent circuit parameters you found back in the lab. And here, V Thevenin, everything is known here also. Because X1, XM, R1, and V1 are all known. Because also the V1 is the voltage applied to the machine terminals, and it's known. You can measure it in the lab. You can find it easily. Most of the time, it is the rated voltage. Okay? So from here, everything is known. You can find V Thevenin and Z Thevenin. Okay? Don't forget that Z Thevenin is basically R Thevenin plus JX Thevenin. Okay? And now we made our Thevenin equivalent circuit representation. And now that easy. We can just apply it here, remember? So we need to just take this part and just replace it by the equivalent circuit of Thevenin. And now your motor equivalent circuit will look like that. Okay? That is R Thevenin now plus JX Thevenin, and here the terminals you have just opened before to find equivalent circuit of Thevenin, and that is JX2, and here is R2 over S. Okay, and this voltage is V Thevenin. Okay, remember now we have just have this the Thevenin equivalent circuit. We have just replacing now this Thevenin equivalent circuit by the old R1 and X1 and XM and the original equivalent circuit of the machine. Everything now is just in series, and that's why we just did all of this from the beginning, just to make it easy for calculation. We don't have XM anymore because we have just have it included on those R Thevenin and X Thevenin. Okay, guys? So the current moving here, we're gonna call it I2, the current going in the rotor, but basically it's one current here moving in everything. They are all connected in series. Okay, so easy now. We want to calculate I2 as a magnitude and angle vector. L equal V Thevenin as the vector also, divided by the total impedance, which is Z Thevenin plus Z2, the rotor impedance, which is X2 plus R2 over S, anything. So this will be here from this V Thevenin as a magnitude and angle, divided by the whole those, so that is R Thevenin plus R2 over S plus J X2 plus X Thevenin. That is your R2, I2, sorry, okay, as a magnitude and angle from this, okay, guys? You want to just find the magnitude of the current I2, okay, I2 as a magnitude. You need to find the magnitude of those vectors. So the magnitude of the numerator V Thevenin will be just the magnitude of V Thevenin, so that is V Thevenin as a magnitude, divided by the magnitude of this vector back in the denominator. You know how to find this for complex numbers, so it will be the square root of the real number squared, which is R Thevenin plus R2 over S all squared, plus the imaginary part squared, which is X2 plus X Thevenin squared. Okay, guys? This is how to just represent the rotor current like here. And easy enough. We just came here all the way down to calculate the torque. Remember, all equal B air gap over omega S, and you just find it to be 3 I2 as a magnitude squared R2 over S omega S. We come all the way here to just find I2 as a magnitude here and place it here in this equation. If you do this, and just have some mathematics work, I will land you with this equation: 3V Thevenin as a magnitude squared divided by R Thevenin plus R2 over S all squared plus X2 plus X Thevenin all squared multiplied by R2 over S omega S. And that is your torque speed characteristics of the three-phase induction motor. Again, it's a little bit complicated compared to our DC machine, for example, because like we said, the math of the three-phase induction motor is a little bit complicated compared to other machines because of this induction property. Okay, guys? So looking at this here, V Thevenin can be found easily from its calculation back. V Thevenin is just V Thevenin here, calculated from this equation here, and it's just totally depending on the V1, which is the voltage applied to the machine terminals. Okay? So V Thevenin is just representing the voltage applied to the machine in a way or another, so that's something mostly constant with the operation, because we don't play with the voltage most of the cases unless we need to control it. Okay? And everything here, R Thevenin, R2, X2, all of that, even omega S, which is the synchronous speed, which is constant as long as we're not playing with it. So everything here should be constant except for your torque and the slips S here and here. And that's how we represent the torque speed characteristics. So this, we call it the torque speed or torque slip characteristics, because you know that. Okay, so the slip equals ns minus nm over ns. Okay, and the synchronous speed ns most of the cases is just constant, so we play, so yeah, the slip totally representing the mechanical speed. So you can use this equation to represent your torque speed characteristics. And from our back experience with other machines, we need the torque speed characteristics because it just tells you how your motor will respond to the change in the load torque, because that's how things done. Okay, how you do this is basically you need here to just draw this relationship. So you get this relationship with an actual machine and just have all those parameters and voltages and just changing the slip with different values and plot the torque. Okay guys, if you do this, you'll land out with the very, very famous shape of the torque speed characteristics of three-phase induction motor. I'm gonna just have it here with the speed on M. Okay, you can find, yeah, so you can just, as it is, you just change the speed and this will change the slip, and you just substitute in this relationship about the slip and find the torque. Okay guys, it will look like that. Okay, that is a very, very famous shape of the torque speed characteristics of induction machine. You'll find it in a textbook. Everything is just playing with it. Okay, that's the curve you can find if you just plot these characteristics, this equation, and just plot the speed versus the torque. I'll find this. Okay, so how to understand this torque speed characteristics? Let's look a little bit. So first of all, this guy have a value here that is the maximum torque you can find here, guys. So this torque, we call it the TPO. What is this? It is the pull out torque. Okay, so this is your pull out torque. Okay, pull out torque is the same like if we can just sometimes we call it the maximum torque maximum, or torque breakdown. They all have the same meaning. That is the maximum torque the machine can handle. After this torque, the machine will break down. Okay, that means you're just having a very, very heavy torque applied to the machine, and that means the machine has to develop very, very high torque. If you just have the torque anyway higher than this value, the machine will just break down. Okay guys, that's why we have on this torque speed characteristics two zones here. Okay, the right hand side zone here, we call it the stable zone. This guy, or this left hand side, we call it the unstable zone, or sometimes we call it the breakdown zone. Okay, so the machine works all the time in the stable zone, because if you want to go over this, the machine basically will just burn. So you start from here and start increasing the torque until you hit this value, the pull-out torque or the breakdown torque. Okay, after this you go to this unstable region, but actually that's a theoretical zone. Okay, you'll not find this in the actual life, because you cannot enter this zone unless you just have a torque higher than the pull-out torque. And if you have any torque higher than the pull-out torque, that means you are burning the machine down. Okay guys, that's why it's almost a theoretical zone. So most of the time we're just playing here in this zone, the stable zone of the machine, like you're just seeing here. Okay, so for this we call it the pull-out torque. For this value, that is the starting torque. Because of this, you have just zero speed, Nm equals 0. Okay, so the speed equals 0 at the starting. So the torque corresponding to this is your starting torque. That is the torque that the machine have at the very initialization. We just hit the start button and the machine start developing some torque to start rotation. Okay guys? Okay, so where is your actual torque the machine working at? So the machine develops as much torque as the load requires. Remember this? This very famous equation we just had before very enormous times. Okay, so if you remember this, the machine's torque has to equal the load torque plus J d omega by dt plus b omega m. Okay, this guy we call it the inertia torque, and just happens at the transient periods. And this we call it the friction torque, because you need to overcome the friction with the mechanical parts, but mostly the torque of the machine has to just be as much as the load requires. Okay guys, so if the load torque goes up, that means you have a higher torque requirements. The loads became heavier, that means your motor torque has to increase to just meet these requirements. Okay guys, so how much the machine actually develops torque, it depends on the load. So which point on this whole curve you're working on now, it depends on how much load you're having at this exact value. Okay, so you have this torque speed characteristics, which is your motor, and you basically have on the same thing, you just plotting the load torque. So for example, this is the load torque, that machine, that is the load torque, that is how much torque the load draws. Now the intersection of both of them will just gives you what we call the operating point. Okay, that is the intersection of the torque speed curve of the motor with the load torque. Okay, and this will give you how much torque actually the motor is just producing now. And from this you can go down here and find which speed, actual speed you're working on now. Okay guys, and if this load torque goes higher, for example is now here, that means your operating point has jumped to be here, and that means your speed will go down here. And when you increase in the load more, you'll hitting here, and that means the speed will be here now. We know that is with the increase in the load torque, the motor torque will increase, and that means the speed will decrease, go down, because acting like more brake on your shaft, like you've seen here. And if more increase the torque of the load more and more, you will hit this point, and if you go down, you see the speed going down and down. Okay guys, like you seen here. So with the increase in the load, the speed as you seen here just decreasing like that. You keep doing that until you hit the maximum load, the pull-out torque, and this will give you here this corresponding speed. And this is the least speed you can just hit, because that is the maximum torque you can develop. More than that, you're just going into the unstable region, and that means the machine is now breaking down. And we don't need this, and we do not let the machine go this. But that's how you understand the torque speed characteristics of the machine, guys. So you just derive the torque speed characteristics and just look at it, and look how actually the machine is responding to the increase in the load. Okay? We'll keep investigating this more the next time, but I hope you just have the whole idea of this stuff. Okay, so just today we just continue talking about the testing of the machine to find the no load test of the machine, which is finding RC and XM, and use the equivalent circuit parameters we just found with our equivalent circuit to derive the torque speed characteristics using the Thevenin equivalent circuit. And now we just have our torque speed characteristics drawn here and started investigating it to understand how actually use this torque speed characteristics to understand how the machine responds to the load change and load variation. Next time I'll be just continuing digging more on this until we understand wholly the performance of the machine when connected to an external load, which is the typical condition of working of such a machine. Okay, thank you guys so much for joining me today, and looking forward to see you next time.